So like I said, we're kind of stepping out even further from our solar system. It's exciting that Voyager is leaving the solar system, kind of between stars. And also kind of related to between stars, if you watch the news, did you hear that there was a spacecraft that got close to a comet years ago? And in 2006, the spacecraft deposited stuff it took while it was by the comet. So that was 2006. So that's what, 8 years ago? And so ever since then, 8 years, they've had like people like us who just going through these photographs of the stuff that was brought back. Anyway, so now they have cycled into or honed in on like 3 or 4 different particles of material that is interstellar material. And what that means is it did come from our solar system. It's like really foreign. So anyway. So let's kind of put things in perspective, starting with our galaxy. So a little bit ago, I said that the planets orbit the sun kind of on a plane. We're going to call that a plane, the frisbee, kind of on one, we're going to call that the ecliptic. Similarly, the stars, like our sun, kind of lie on another plane, making what we call the Milky Way galaxy. Okay? So I'm not even going to click that power, so 10. To kind of pull together, there's Earth, recognize Earth, okay, big little blue marble, okay, and that kind of the second image down there is our solar system. Okay, so stepping out then, the box above our solar system would be the Milky Way galaxy. And then the box above, these are just artist renditions, the box above the Milky Way galaxy is actually showing you how galaxies are grouped together. Do you see the word local group? Okay. Anytime you hear the word local group in astronomy, they're talking about a set of galaxies. And the Milky Way is a member of the local group. And then clusters like the local group are further organized into superclusters. I know it's weird, it's clusters and superclusters. Okay, just more organization. And so when they go to map the universe, it kind of takes on actually kind of, can you kind of see this webbing in the back there? That's kind of an artist's impression of the data we're getting back from what does the fabric of the universe from our perspective look like. So those little dots would be galaxies. And galaxies are grouped into clusters, and clusters are grouped into superclusters. And they're all around these kind of big voids of nothing. So it's just kind of mind-boggling. It's beautiful, is what it is. Okay. So speaking of galaxies, okay, our galaxy, the Milky Way galaxy, if you ever seen somebody said, oh, there's the Milky Way in the nighttime sky. Okay, what they're talking about, and I'll kind of dim the lights, can't see it very good, but the Milky Way, the way it got its name, honestly, is because it kind of looks like spilt milk. It's a band, though, and I have a slide here, I think it might be the next slide to show you, that what you're doing is you're kind of looking into the frisbee, the plane of our galaxy. So that band is where it's the hot spot of stars, okay? So this one over here on the right, that's just kind of a bird's eye view. We've never been above our galaxy, but we believe it's a spiral galaxy. We can see that spiral structure in other galaxies.
So that's not an actual picture?
Right, that's not an actual picture. It's what they think it would look like. Oops, did I skip one? No, I guess not. Okay. So, I don't know if you can see it, but there's Orion over there. Let me go ahead and grab a pen, okay? The constellation Orion, which should be coming up in a month or so, it's beautiful. Constellation Orion has that characteristic 3 stars that are kind of set equidistant from each other, and that is Orion's belt. From his belt hangs his sword. But the other thing is characteristic is kind of, I'm pretty sure that's his toga. You know, togas have like a thing, and then those would be his knees. It's kind of near his shoulders and his knees. So that is Orion. So one of the, I'll refer to your map. Oh, I think I might take them all away. But the sky map I gave you, it says one of the things that you can find are nebula. And actually, if you look in the sword region of Orion, there is an assortment of nebula hiding out there. In general, this is what a nebula is. Okay, in general, a nebula is a region of space that is not void of material. Okay, a nebula has dust in it. And I was just listening to a podcast on the way to work this morning talking about dust in outer space. And when they say dust in outer space, they're talking about little tiny rocks. So there's different types of dust regions out there. The word here, planetary, okay, planetary nebula is one type of nebula. They have nothing to do with planets. They do, but they don't. They got the name planetary nebula because they look almost like they have a substance enough to almost to, if you don't know what you're looking at, would be a planet. Okay, but they're not. So these are planetary nebula, and each one of these, and kind of see that in the middle there, each one of these have a star that has died and given its material off like that. These are planetary nebula. Nebula because it's dust. What it come from? A star that's dying. Kind of sad. But the stuff that star gave off can be fodder for another star being born from. That's good. Okay, galaxy. Now this is a photograph of the galaxy that's closest to us, the Andromeda galaxy. And actually there's 3 galaxies up here. I think 3. This looks like one of its companions, and I'm not sure if that's one of its companions or not. But there is the Andromeda galaxy. I'll go ahead and take a minute to kind of tell you that, do you guys see this M31 down here? Okay. So, M is like a catalog. So in astronomy, if you ever see, oh, it's got an M number. Well, it's a catalog, and there's a bunch of M's. And actually, M's go from 1 to 110. And here are the M things. And the M is actually short for the scientist Messier. It's French. Okay, so each one of these boxes is a Messier object. It's kind of fun how this worked, because back in, I want to say the 1700s, he actually wanted to find comets. So he's looking for the fuzzy little comas of a comet. And he kept running up against these things. And he thought they were annoying, so he finally had his grad students categorize or catalog them. So, you know what I'm saying? There's 110 of them. Yeah. And they're different things. In a minute, I'm going to talk about star clusters. Some of those are star clusters. Some of them are nebula. Some of them are galaxies. So M31 is right here. On a given night, sometimes they'll put something in a telescope in an observatory and they'll say it's M blah. I'm like, oh, okay. Okay, so star clusters fall into 2 categories. Anybody ever seen the Seven Sisters? Okay. 7 Sisters, otherwise known as the Pleiades, and they actually are I want to say 57. So star clusters are a group of stars that were born about the same time, so they are like really near each other. Sometimes stars look like they're near each other, but they're not. These are near each other. So this is an open cluster. And this is an example of a globular cluster. These are my favorite. These globular clusters, and some of them are tight, some of them are spread out, and they look 3-dimensional through a telescope. Okay, so if you look at what Messier found, okay, some of these are clusters, star clusters. And like if somebody says, oh, let's look at the butterfly cluster, what somebody says is that's an open cluster, it happens to be an open cluster that looks like a butterfly. See what I'm saying? You go in this butterfly. There's a duck cluster, a wild duck cluster. Okay, so open clusters and globular clusters. Okay. So, let's see, I don't think this is very long. Let's see what this is. I'll go back. I haven't had very good luck with YouTube videos. But our snacking black hole does a good job. Ooh. You're going to be blasted out.
Now, the termites over here.
We headbang into heavy metal music.
Yeah. Everyone loves black holes. Unless you're getting eaten by one.
In deep space, sending dozens of stargazers scrambling. Whether they're seasoned pros or high school amateurs, their goal is the same.
Got a camera, folks?
Really?
We need to move the dome, Casey.
To catch a glimpse of a star in its final death throes.
That's amazing. It didn't do what I wanted it to again. I promise. I usually have better luck at YouTube videos.
The diamond at the center of the galaxy. Presented by Science at NASA. Deep in the heart of the spiral Milky Way galaxy, a hot vortex of matter swirls around a black hole more than 1,000,000 times as massive as the Sun. Many galaxies, perhaps all, contain such a monster in the middle. These supermassive black holes sustain themselves by swallowing stars, planets, asteroids, comets, and clouds of gas that wander by the crowded galactic core. NASA's New Star spacecraft recently caught the Milky Way's central black hole in the act of having a snack. We got lucky and captured an outburst from the black hole during our first observing campaign, says Fiona Harrison, the mission's principal investigator at the California Institute of Technology. New Star is an orbiting observatory designed to take pictures of violent, high-energy phenomena in the universe. Launched on June 13, 2012, it is the only telescope capable of producing focused images of the highest energy X-rays, produced by the remains of exploded stars and ravenous black holes. It's like putting on a new pair of glasses and seeing aspects of the world around us clearly for the first time, says Harrison. New Star's sharp vision allowed it to pinpoint a burst of hard X-rays coming from the galactic center during an observing campaign in July. Lower energy X-ray observations by NASA's Chandra X-ray Observatory and infrared data from the Keck telescope in Hawaii confirmed the outburst. The Milky Way's black hole had just swallowed something. Black hole snacks are a violent process in which the meal is ripped apart by powerful tides, produced by their extreme gravity and heated to millions of degrees as they slide down the gullet of the gravitational singularity. In this case, New Star picked up X-rays emitted by matter being heated up to about 100 million degrees Celsius. The observation raises the hope that astronomers will be able to help solve a long-standing mystery. Why is the Milky Way's supermassive black hole such a picky eater? Compared to the giant black holes at the centers of other galaxies, the Milky Way is relatively quiet. More active black holes tend to gobble up matter in prodigious quantities. Ours, on the other hand, is thought only to nibble or not eat at all. Asteroids could be a primary food source. One model holds that trillions of asteroids surround the Milky Way's core. Astronomers using the Chandra X-ray Observatory have indeed detected flares consistent with asteroids 10 kilometers wide, larger, falling into the black hole. These space rocks would be about the same size as the asteroid that wiped out the dinosaurs on Earth 65 million years ago. Smaller space rocks might be falling in too, but their flares would be too weak for Chandra to detect. NuSTAR's capability to detect flares above the energy range explored in the past opens a whole new window on this problem and provides astronomers with a powerful new tool for understanding what's happening deep in the core of our galaxy. The monster's menu might soon be revealed. For more focused, high-energy news from the center of the Milky Way and elsewhere, stay tuned to science.nasa.gov.
Ah, that's what I wanted to show. So did you catch that most galaxies, we think, have a black hole in the center? But if you follow astronomy and all that, you know that that's not the only type of black hole. There's another common type of black hole. When a massive star ends its life, it can leave a black hole too. Okay, so that's the supermassive black hole, galaxies. If a star dies and leaves a black hole, we call that a stellar black hole. So you're like, black holes hurt your brain, they hurt my brain too. But what those two black holes have in common, basically, is to take any ordinary matter. You could take a cup, styrofoam cup, and if you took those molecules, if you took the material itself and squished it down to a certain squishness, a certain density, you could turn that cup into a black hole. True. So kind of along those lines, I'll talk off and on about there's things called particle accelerators, and it's a physics thing, and there's one called the CERN, C-E-R-N, particle accelerator. But basically, what it does is it's like 17 miles maybe in diameter. It's in Switzerland, and so they have two particles, and they collide them. So they make it go fast a few times, and then they open up the gate and let them roll. Particles run into each other. Those particles could be like electrons or protons, run into each other. And so I mentioned that black holes because that was kind of with CERN was like, oh my gosh, they're going to basically squish that matter down to the point to make a black hole. And it's never happened. So that's about black holes. And yes, they do hurt my brain too. These would be photos. This is M13 again, Andromeda Galaxy, and these are some other spiral galaxies. Okay. So I switched the order of the next couple of slides. So hold your hats. But if my slides don't match yours, let me know. But I think just kind of hold your slide. Hold your hat for now. So, like in physical science or like in chemistry, if we're studying on something or studying a chemical reaction, we'll usually use a beaker, and we'll call that stuff in the beaker. We'll call that our system, okay, of interest, okay. And then outside the beaker is the surroundings, okay. And then we would say the universe is the system plus the surroundings, okay. That's the universe. So in astronomy, we basically say the universe is any and all matter and energy. That's the universe. Okay, you can't look at anything and say you can identify it entirely in terms of matter and energy. That's it. Makes you feel kind of, So that's what astronomers are looking at, a balance between those, or what's up with matter and energy in the universe. Okay, so I'm building up to, and I meant to put builds on here. You don't have this slide. Yeah, you don't have this slide. So just, I don't know what you want to put down, but I can get you the slide next time. Would that be helpful? But this is my attempt to kind of talk about how we use a year as as a distance, because you know usually we use like a foot, that's a distance, an inch, that's a distance, okay? And so here's the deal. For instance, let's say you're driving a car, I meant to do builds, so don't look at the bottom one. You're not going to drive that fast. But let's just say you're driving the car 60 miles per hour, okay? And somebody says, well, how far are you from here? And you say, I'm 30 minutes. Like, okay, so you did a time for distance, right? Okay, so you must be 30 miles. Does that make sense? Okay, you're doing 1 mile a minute because you're doing 60 miles an hour. So if you're 30 minutes, you're 30 miles. Does that make sense? So you just took a time based upon how fast you're going and translated it to a distance. So let's say you got a faster car. Let's say your car, and I don't know if it's possible, you're traveling 600 miles per hour. You jacked it up. Okay. So instead of being, and if you say you're 30 minutes away then, you would be 300 miles away. Does that make sense? Okay, good. You're 300 miles away. Okay? Does that make sense? So let's say you're going even faster. Let's add a couple of zeros, several zeros. Let's say you're going 6 million miles per hour, and you're 30 minutes away. Okay, so that puts you at, doing this pattern, help me out. That puts you at 3 million miles away? Okay, good. So you just used a 30-minute time. Okay, that's how far, and you translate it to a distance. But all that is based upon you knowing how fast you're going and giving a time. So by the way, there is did you guys know that you can use Google and have it like convert units? So miles per hour, that isn't like what we do in astronomy, but you're going to see here in a minute the speed of light in kilometers per second. So if you want to convert 6 million miles per hour into kilometers per second, there you go. There's your number. There's how fast your car's going in kilometers per second. Oh, about 2,600, 2,700. Okay. And back to the show. Alrighty, so now you should have this slide. So we've known for a while how fast light travels. And it's kind of neat because early on, they found there was some calculations done based upon moons orbiting Jupiter, okay, to know how fast light travels. Just to kind of make a point, if you're like me, when you turn the lights off and then when you turn them on, you think, well, that didn't. You think the light gets to you right away, but there's a delay, okay. And so based upon how fast light travels, if there's an object sending us light, like a star or a planet or a moon, okay, if it's sending us light, and we know how fast light travels, if we know the time it took, okay, to get here, then we really kind of know a distance. So what we do is talk in terms of how long it took light to get here. So for instance, when the moon shines on us, of course, it's the sunlight hitting the moon and then that light coming to us, okay? It takes 1 second for the light to go from the moon to the earth. I did the math. Little factor label problem. Okay? So we would call that 1 light second. 1 light second. Okay? And in terms of kilometers, you're looking at 300,000 kilometers. So now the other thing I've done is we'll talk just a little bit about what's called scientific notation. Okay, this second number down there is 300,000 packed up in scientific notation. Okay, and I'm not gonna, you're not gonna do any math problems. But but the bigger that number, the 5, 10 raised to the 5th power, the bigger that number, the more the zeros. Okay, that's what you need to know. Okay, so when light leaves the sun, it takes based upon its traveling speed, it takes 8 minutes to get to the Earth. Well, the distance between the sun and the Earth varies a little bit, but on average, 8 minutes. Okay? So that's actually why when a solar event happens, it takes 8 minutes for us to know what occurred. It takes 8 minutes for us to get fried if it's charged particles. But so in terms of distance, and I just went ahead and packed it up into scientific notation, the 8 superscript of the 10 means you have to move that decimal over 8 places. So you got, what, 7 zeros after the 4. So that would be 8 light minutes. So 8 light minutes. That's how far away the sun is from the Earth. The closest star to us, is that the closest star? Oh, no, it's just a bright star. 8 light years away. The closest star to us is, did you guys see that movie with tall people? I don't know if they were blue or not, but very popular movie.
Avatar.
Thank you, Avatar. Yeah. What star was it around? It wasn't Sirius, I think. But that's the closest star to us. And it takes 8 years from that star to get to us. It's just a bright star. It's a dog star, Canis Major. 8 years, I know. And see, to me, you should, and the energy of light is called photons. The energy of light, let's see, how do I say that? I think that's okay. Light travels in packets called photons. So for those photons to get to us took 8 years. So better appreciate those photons. So that's how far it is in kilometers. Well, you know where I'm going with this, and this is the last one. Our closest galaxy to us. So we have the Milky Way galaxy, and Sirius is in the Milky Way galaxy, seriously. Okay? And then the closest galaxy to us is Andromeda. And it is 2.5 million light years away. 2.5 million light years away. So in terms of kilometers, you have to move the decimal place over 19 places or add 18 zeros to 24. That's far away. Okay. So when we look through the telescope, or when these pictures were taken, I mean, it took the light 25 million years to get to that optical device. I know. And then this is where people will be like, well, does it still look like that? I'm like, probably not. I mean, it ages, but we're not going to know it because there's a delay for us to get this stuff. Okay. So we're seeing objects in the past. Not only that, but if an object is farther from us, it takes longer for its light to get to us, so it's older. Okay? The farther away an object is, the older it is. So this is why I kind of moved some things around while it's coming up. So finally, and I've been kind of talking about a light year, a light second, a light minute, 8 light minutes. Okay? So when somebody says that something is 1 light year away, it is a distance that light travels in 1 year at that 300,000 kilometers per second. In terms of miles, it's about 6 trillion miles. Okay. So here is a cute little observatory. Okay, telescope in here. The thing about observatories is this lid on top kind of moves around. I love that sound. It goes, okay, and there's a slit in the top, it's protecting the telescope. And you put the slit where you want to look. And so kind of looking back at 3 different objects, okay, maybe this galaxy is 7 billion light years away. 7 billion light years away. So it took 7 billion years for it to reach us. Now, I'm going to throw some dates at you, throughout the course. And we think, let's see, by more than one method, the universe, I'm just going to go ahead and kind of crudely say, it is, what did I say? Darn it. I didn't look it up recently, but I'll go ahead and put 13 billion years old, the universe. And that's alluding to something, an event we'll talk about, probably coming up briefly, called the Big Bang, 13 billion years ago. Our solar system has to be younger than that, right? Our solar system is about 4.6 billion years old. So here's the deal. You know, with our telescope, oh, I better jack this up. I wasn't very good. Let's put 14 billion years old. Drat. I changed that 13 to 14. And you see why? I think that's why. Okay, if our universe is only a certain finite age, okay, then you can't see something farther than that because it's older than that. Does that make sense? Okay. It's interesting. This over here is what we call, let's see if I can kind of hone. That edge over there is what we call the cosmologic horizon. Cosmologic horizon. Now you see why I use PowerPoint slides, because my writing is terrible. Cosmological. There you go, horizon. It's the edge. Some would say, and if you're like me, watch those documentaries, would say that there are multiple universes out there, and I think it makes sense. But okay, so this was the slide that I moved later because it made more sense. Okay, so a couple of sets of pictures here. This one actually is some galaxies that are about 8 billion light years away. Okay, and this is a set of galaxies that are about 13 billion light years away. One of the things about, we talk about kind of the life, the old galaxies versus newer galaxies, is these old galaxies look kind of, I don't know if you can almost kind of see, they look a little more chaotic. Okay? They look a little more refined. Gravity has set in. All right. So we're kind of finish up, kind of switching gears. It's like to go from the cosmological horizon back to the Earth. You're like, really? So these last set of slides kind of talk about how we're always moving, and this is where I kind of smile if, you know, you have these squirmy little preschoolers like, can't you sit still? And they couldn't see a smart answer, no. So we're going to talk about motion, movement. And we'll be talking more about rotation. The Earth rotates or spins on its axis, and revolution or orbit. We'll be talking more about that. But rotation is one motion. One of the things I think is interesting, if you consider rotation by latitude, so hopefully you guys are okay with, these would be lines of latitude. You know, as far as spinning goes and motion, if you're at one of the poles, you're not moving with regard to that spinning. That kind of hurts my brain too. If you're at the equator, you're really spinning. You really have a lot of motion. Okay, so that's one motion. What else we got? Okay. There's too many R's. So rotation, okay, spinning, and revolution. Okay. So if I go ahead and put my trash can as the sun this semester, back in the middle of the room. Okay. And let's see. I need to bring a sticky note to mark north, because north's really important. Okay. Because you see that, well, before I talk about why north is so important. Okay. And I didn't emphasize it necessarily as much as I should have, but do you see the AU? Okay. A light year is far. Okay. An AU is another important distance. An AU stands for astronomical unit. And if I'm the Earth and that's the sun, Earth and the sun, 1 AU is that average distance. Now we're going to see that it's not always the same, but that's 1 AU, okay? All right. What else we got? All right. Why north is important? This is why north is important. Because the Earth's axis axis of rotation, and see it's pointed, but that's not north. Okay, this is north. So the Earth spins on, let's say the Earth, and I'll get something longer next time, yardstick, but let's say this is the Earth's axis of rotation. It is always tilted towards one place, okay, and that's north to us. Actually, that's our North Star. If you were to go dot, 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 it would touch Polaris. Okay. Anyway, so see if you can kind of catch this. So once a year, the Earth orbits or revolves about the sun. Okay, so let's see if you can see my tilt. Okay. And I'm going to keep it like tilted. Okay, now it's rotating once every 24 hours, but I've just done like 6 months, haven't I? Okay, another 3 months. Another 3 months. So I bet you by this we'll talk more about the whole winter-summer thing. But we're in the northern part of the Earth, okay? And can you see where this actually would be our winter time? This is the winter solstice. Okay? And 6 months later, this is the summer solstice. Got this tilt thing going. Okay, but that's another motion. It's kind of the point here. All right. And I remember I said counterclockwise. You can't go wrong answering counterclockwise. So and if you ever see me go the wrong way, let me know. So not only do the planets orbit the sun counterclockwise, but most of them spin counterclockwise on their axis. So does the Earth. Most of them. Well, we got more motion. Oh my gosh. So this is kind of trying to show you what we call a face-on view of the Milky Way galaxy. Okay. And as it turns out, it's kind of nice because, just like the Monty Python song says, we are actually kind of halfway between, there's a black hole there, remember? Halfway between the black hole and the edge. Okay. So we're there. And like the first thing says, is that in our region of stars in the Milky Way galaxy, the sun is kind of bobbing up and down a little bit. Do you remember the 2012? Like, ooh, oh, the Mayan calendar. I know. I just got a little excited about it, but the thing about it is that I think that had to do somewhat with our star, the sun, is kind of going in and out a little bit of the plane of the Milky Way galaxy, and there was some alignment there. It's a stretch. Okay. All right. So, not to worry though, we're not going to get like seasick or anything because we're bobbing up and down, and the stars in the vicinity in the Milky Way galaxy are bobbing up and down, but we can't even tell it. Okay. But the other thing, and this is not a random motion, if you look at the yellow or orange, whatever this is, and it's showing clockwise, which I think that's okay because now we're talking about our galaxy, not our solar system. But all of the stars are going around like this, okay? Gravity requires that stuff that is gravitationally bound, for instance, a black hole, it keeps moving. It's got to keep moving. Move or die, okay? Okay, so all the stars are making a path like this. And so the sun has been where it is about 230 million years to complete one orbit around the Milky Way galaxy. So that's another motion. Motion, by the way, has, remember I said you either keep moving or you die sort of thing? Okay, kind of related to how fast everything's moving. They can do a calculation to understand where the weight is. Where's the matter that's making that motion happen? And when you do the calculations, the weight is not where they think it is, basically. Stars have mass, stars have weight, right? Okay, but what they're finding is that this mass is like what we call the halo region. Let me go ahead and kind of highlight that. Okay, so what you're looking at is this is the edge, what we call an edge-on view. I like red on black. Isn't that pretty? That's the edge-on view of the Milky Way. Okay, and again, I'd like to say, I don't think this is the artist's rendition. And so up here is the halo region. We have halo above and below. And based upon motion, again, what they find is that there is a lot of mass in the halo region. A lot of mass that's not stars in the halo region, outside of the plane of our galaxy. We'll talk more about this too. But if you've heard him talk about dark matter, that's dark matter. Okay, you just don't see it. All right. I have one more motion, is that, let's see how I'm going to say this. There's like, the fabric of space is expanding, but that's not what this is. This is basically all galaxies are moving away from one another. All those pictures of galaxies we saw, they're all moving away from each other. How would that work? They're moving away from each other, they're moving to something. Or something, they're all moving away from one. No, they're all expanding. And this is kind of a common way we tend to kind of look at it. I've not really ever had raisin bread before, but the raisins are just kind of nice. You can see them move. So let's say you had a cookie or raisin bread, and when you bake it, all of those raisins kind of spread apart from each other. And then what's done, or what your author did, is identify one of those raisins as us. Okay, we're the local raisin there, and we're the local raisin here. Okay? And if you were to look at your neighbors and kind of see before you baked it and after the whole thing expanded, okay, your furthest neighbor, actually, you're going to see is moved the farthest from you. Why? Because everything's running away from each other. Okay? So, in fact, it's kind of summarized over here. The furthest one, which is raisin number 3, okay, after the cooking, okay, it took an hour to cook perhaps, it moved 6 centimeters, so 6 centimeters per hour. Okay, the middle raisin moved 4 centimeters per hour. The closest raisin to the local raisin moved 2 centimeters per hour. Okay. So that's what we call, when something moves like, let's see, when you get married, recession, okay, but when you're moving away, it's recession. We call it recessional motion. So the recessional motion of the farthest one is moving faster. So the universe is expanding. Okay. So I don't know what you need to add here. It's kind of like the furthest raisin was going the fastest. And I don't have it on the slide, but we're going to see, well, how do they know that that raisin is going faster than the closer raisin? And if you have ever heard of the technique called redshift, that's kind of how they do that. They look at the kind of the blur, the redshift is greater for that farther galaxy than the closer galaxy. Okay. The last slide about? Yep. Pretty good. Okay. So if I ever ask you on a test, hint, hint, okay, how are we moving? Okay, hopefully you can kind of pick an assortment of one of these. I mean, these you already knew. You already knew a lot of the stuff before you came to this class. For instance, the Earth is spinning on its axis of rotation. So as long as you're not at a pole, you're okay. Okay? So the Earth rotates on its axis. Okay? The other one is that the Earth orbits the sun. Those are both favorite ones. So these are all motions in space. The next one is kind of showing you kind of the bobbing up and down of the sun amidst its neighbors. Okay? The next one, the yellow circle, is showing you that our sun takes, 270 million years to complete one circle. That's pretty cool. And then the little green arrows are trying to show you the expanding universe, I want to say. Well, maybe not. The last one's expanding universe. So, and that's where I wanted to get to. It's about 20 after? Yes! So I will post those, hopefully with, I'm hoping, I don't know, I can't decide. I'd rather have the newer figures in the slides that we're going to do next Thursday, but I don't know when I'm going to get those files. So I don't know. But when do you guys need to have them to print them? Like, today is Thursday.
We can print them before class, I mean, we can't really do that unless we get the bill in the blank.
Yeah. I will send you an email when they're available. How's that? So you don't have to keep checking, like, did you put chapter 2 up? No? Okay. So we'll do it that way. In the meantime, chapter 1 questions are due next week. Are there any questions about chapter 1 questions? Okay. All right, let me know if you have any questions this week. But otherwise, have a good one. And I was looking to see if it's clear or not.
One question says this chapter, and how this book, is that correct?
Yes.
Okay, and then the question you want us to answer the book number, like the 2, 3, 6, 10, 12. Is it like we read this?
Did you miss it? Yes. I missed the first one, but I was kind of excited.
These notes.
Page 3. I can't read the handwriting, just tells me. So when we come back Thursday, we need to have chapter 1 read or chapter 2 read. That's what I don't I'm not sure.
Well, I don't give reading assignments per se. If I was, it depends on how you learn. If you want to read it before or after we have it, I think I'd always rather.
Or we read we do read the whole chapter, or we go by this stuff, right?
That stuff is kind of like something for the.
Well, I already read the first chapter, and everything I did was in the first, was basically like, I didn't even need to read it. It's all here. I just read it because I was bored one day, and
It's a neat book.
yeah.
She's an overachiever.
No, I just
Here
you go.
But like,
Hers were all
really kind of set up, honestly, that if you're attentive and effective, and if it works for you, you know, I cover everything you need to know.
Yeah, you
For the
did
test. And I
everything.
try not to test you over anything.
Usually use them front
Yeah,
and
I do.
back.
So only
Yeah,
if I cover it.
but I couldn't figure it out because it brings it up as a Adobe reader opposed to
Hours, I can't get, I have
So when you,
well.
when you
I have a
print
friend
it,
that
it'll
has,
just
you
print.
get the questions from.
Yeah.
It's a good type, but it is expensive.
It is, I rented mine. Yeah, even renting it was
Oh,
like
don't forget your phone.
Yeah, but you know what, you get, I don't know how much of that you get back.
I think because it's the first week I've been back in today. I
Well, I
started
took
out
one
in
of my books
Burlington
back
at
today, and they
9
told me that the $52 I paid for it to rent it was going back on my account.
Doing classes or?
Yeah.
And I'm so, unless you don't return it, I don't think you get charged.
And during the summer, it was
Okay.
like.
You look
That's
pretty
the way I
bright.
took it today. I may be wrong, but I took a flux class, and, I just didn't, yeah, because I don't like the books laying around my house. So I took it back today, and that's what she said. She goes, well,
So now my whole.
that money will go back on your account. I'm like,
Crazy.
so I guess,
Anyway,
I should have.
I was kind of looking into the book
but
and I didn't realize the astronauts, you know, it was talking about them.
That's the way I
looking
look at it.
around in the ship and stuff, because there's no gravity.
Which if that's the case,
Yeah.
it's
Yeah,
totally worth
and
it.
that's so
Renting
interesting.
every book that you can than buying anything because book buybacks.
Yeah, you can't
Have a nice
buy,
weekend.
like,
Thank you.
some of the ones that I got, I was able to rent, like this one, but some of them you can't, you have to buy them, like the public speaking book, you have to buy.